unmute myself.
Yeah.
Okay.
Exactly.
Is the sound working now? Yeah?
Yes.
Confirmation? Okay, good. Okay, great. I'm glad we caught that early on. Okay, so is cognitive technologies. And when I say technology, the Cartesian coordinate plane here is one prominent example. It was seriously a breakthrough when it came out just a few hundred years ago. The way of linking algebra and geometry helped to resolve mathematical puzzle that actually stumped the world for thousands of years. And the coordinate plane you can think of as a technology because it was invented by people, and a cognitive technology because its main purpose is to help us grasp new ideas and work with them more effectively. Now, not only have these kinds of tools or technologies been for thinking been useful in mathematics, but they've also been major drivers of scientific progress across a bunch of different fields. So each of these iconic images captured some new way of looking at and understanding the external world, from Darwin's finches on the top left here to the Feynman diagrams in the bottom right. Now notice that some of these pictures are quite detailed, but others are quite a bit more abstract or schematic. Yet what all of these examples share in common is that they leverage visual abstraction to link our observations, our direct observations, to what we know in a format that's useful for thinking and communication. Now, of course, all of these extraordinary feats of human collective learning weren't achieved overnight. They actually build, of course, on many generations of continual learning. And this is something that was greatly accelerated by people discovering about 30 to 80,000 years or so that they could mark up their physical environments. So in this iconic example, these cave walls, repurposing objects and surfaces in their surroundings into carriers of meaning. And so one of the fundamental questions that my lab wrestles with is what explains why the externalized abstractions that people create take the form they do. And this is a diagram that I use to help me think about the key entities in play. So there's a person who makes an observation about the physical world. That person then inscribes that observation in some way, which in almost all cases nowadays takes the form of text or a graphic. And then there's a receiver, one or more receivers, who interprets that artifact, that picture or bit of text, and then takes some action in the world. And our core hypothesis is that even the fanciest of our cognitive technologies, the ones that we use today, whether we're thinking of like a stone tablet or modern computing systems, are at the end of the day grounded in the need to coordinate visual and motor behaviors in the service of concrete behavioral goals, in particular, communication and coordination with other people. And so our challenge is to develop a theory of how this alignment can be achieved between the contents of perceptual experience, the actions we can perform, and expectations about what other people will understand. And so today I'd like to propose that this alignment relies upon what I'll call bridging abstractions. Okay? I'm calling these bridging abstractions because they're the representations that lie at the crossroads between visual perception and motor execution. And in the context of trying to account for how people create meaningful images or text, the form these bridging abstractions take is assumed to be constrained primarily by a communication goal. In other words, to make sense. So here are the top level questions that I aim to address in this talk. What are bridging abstractions and why are they important? What characterizes the abstractions that people create? And why do these abstractions take the form that they do? My plan is to offer a high-level overview of two ongoing lines of work, digging into the kind of multimodal generative behaviors that have been giving us insight into the nature of these bridging abstractions. So first, we're going to focus on the use of visual abstraction to create meaningful pictures. And second, the use of linguistic abstraction to convey the structure of objects, okay? What makes visual abstraction such a useful domain for our purposes is that it naturally relies on three behaviors that build successively on one another. First, visual perception, the problem of how we transform raw visual inputs into meaningful perceptual experiences. That in turn makes it possible to think about what visual production is, the ability to generate a set of markings that leave a meaningful trace in the physical environment. And these come together, of course, during visual communication, how we decide just how to arrange those marks and in what order in order to inform, teach, persuade, or any variety of other communicative goals that we might have. To get off the ground with the perceptual question, we started by considering maybe the most concrete and familiar kind of picture, okay? Simple line drawings that are meant to look like something in the world. Okay, so what makes it so easy to tell that the drawing on the left is meant to correspond to the realistic bird rendering on the right? Now, there have been basically two dominant ways of thinking about this problem of pictorial meaning. The first is that we see drawings as meaningful and representing things because drawings simply resemble objects in the world. Like, in other words, the drawing literally looks like the bird. The second is that drawings denote objects as a matter of convention. And we only really learn what drawings go with what objects from other people. So take this Chinese character, for example. So in an earlier line of work, my collaborators, Dan Yeamans, Nick Turk-Brown, and I discovered that general purpose vision algorithms, in this case, neural networks that compose multiple layers of learnable spatial convolutions, were capable of providing a pretty compelling basis for explaining how and why we perceive line drawings, even when they're as sparse as they are, look like objects. But of course, quickly ran into difficulties applying that approach to the wide range of other kinds of pictures that people use. So take this set of whiteboard doodles, for example. A static deterministic account of visual processing really falls flat on its face when trying to explain how we generate and make sense of these diagrams. Like, what these blobs and boxes mean really depends on what you're talking about. So our next goal is to figure out how to incorporate that information about social context to begin to account for the sheer variety of graphical representations that people in fact use to communicate, ranging from more faithful illustrations like those on the left in this diagram, and ranging to the more obviously symbolic tokens on the right-hand side of the slide. And in our first study tackling this issue, we asked how people know when they need to produce a faithful drawing and when they can get away with something more abstract. So in this study, we paired people up to play a drawing game over the internet. The sketcher saw a display that looked something like this, where their goal was to draw the highlighted target object. So in this case, the bird there. And then we varied what the other objects in the array were. So on close trials on the left here, the distractors all belong to the same basic level category. And then on far trials, the distractors were all from different categories. And that was it. That was the only manipulation, okay? And based on that really, really simple manipulation, we discovered just how flexible ordinary people, like, bear in mind, these are not people who identify as visual artists, but these are people who are nevertheless really flexible, trial to trial, in how they use drawings to communicate, making more detailed drawings on those close trials when they needed their drawing to uniquely identify a specific exemplar, but then sparser drawings on those far trials where they could get away with category level abstractions. And then to capture that behavioral flexibility, my collaborators, Robert Hawkins, who gave a talk yesterday, Mike Wu, and Noah Goodman, and I proposed a computational model of the sketcher that used a convnet to encode visual inputs into a generically abstract feature space. And that was nested within a probabilistic model that inferred what kind of drawing to make depending on the context. Basically, a drawing that was detailed enough to help a viewer know which object was the target that the sketcher had in mind, but then no more detail than necessary. And while we were doing this work, the notion of bridging abstractions hadn't yet occurred to me, but you can think of this model as implicitly having learned one in the course of needing to transform a purely image-based representation, form the kind of input into the sketcher, into a format that could then drive decisions about what kind of drawing to make. I wish I had the time to share the full details of our modeling experiments, but in the interest of time, I decided to compress this and spend more time talking about newer work. But the take home from this study was that both the capacity for visual abstraction, which we operationalized as network layer in our visual encoder backbone, which was the neural network. So both visual abstraction and a sensitivity to context were critical for capturing how people manage to communicate about those objects at the appropriate level of abstraction in the Pictionary game. And then in a more recent paper now in press, we've pushed this idea even further to understand not only the impact of the current context on how people communicate using drawings, but also the conditions under which new graphical conventions emerge. When memory for previous interactions with the same communication partner leads people to produce even more abstract, maybe even proto-symbolic tokens over time, whose meaning depends more strongly on context. And if people are interested, I'm very happy to talk in Q&A or go into more depth. Now, up till this point, we'd just been considering pictures, drawings that convey information about object identity, but people possess much richer knowledge about the external world than just what things are called, what they look like. A really important way that we use visual abstraction, especially in science and engineering, is to transmit mechanistic knowledge about how things work. So what's going on in people's minds when they make this move, going from what is communicating what's visually salient, let's say about a specific bird, to going to highlight underlying physical mechanisms, say how birds achieve flight in general. So in work led by Holly Huey, a PhD student in my lab, and in collaboration with Karen Walker, we found that when people produce visual explanations for a machine that they just learned about, rather than ordinary depictions that are meant to just illustrate what a machine looks like, they actually reach for qualitatively new graphical elements, including arrows to convey motion and causal interactions between parts of a machine, even at the expense of preserving visual fidelity to the target object. And what this suggests is that however it is that people are encoding information from direct experience with the machine and how it works, it's clearly a flexible enough mental representation that it's able to support really different readouts in the service of different communicative goals. Cool. And altogether, what these different studies show is that there really doesn't seem to be a single set of bridging abstractions that are needed to explain visual communication, but rather the contents of this teal box in the middle can shift dramatically depending on what a person's communicative goals are in the context that they're in. Which raises the question, like, what are those bridging abstractions that actually support that kind of flexibility? So the modeling approach that we used in the 2019 study, the close and far conditions in order to capture contextual flexibility, was quite limited in many different ways. It relied on a way of linking perception to decision making that relied on a very heavily supervised forms of learning. And it wasn't able to capture the internal structure of these pictures, the inherently compositional nature of those drawings. And it also displayed really weak out of sample generalization. So these are some problems, limitations of the approach that we took. And the problem, I think, is that we've been ignoring all of this rich analogical structure that objects and sketches share, in which the relations between parts of an object, for example, the space relations between the beak, wings, and feet, correspond to the relations between those same parts in a sketch of that bird. In other words, that the units of action that people take, that they perform when producing a sketch, like every pen stroke they leave on the canvas, are quite closely coupled to units of meaning, the parts of the object that they think are relevant to include. So one direction that I'm really excited about pursuing in future work is to take, to really unpack what those bridging abstractions are, which might mean developing what we'll call more weakly supervised or self-supervised approaches to learning how to represent these objects that are inherently compositional, and expose the detailed mappings between parts of sketches and parts of objects that might endow it with the right kind of inductive biases to generalize to other data, like other stimuli and other tasks, so other kinds of behavioral settings. Cool. Okay. So all of those same goals, when it comes to how people use drawings to communicate, as a case study in visual communication, also spurred us to begin exploring our other major cognitive tool, written language, okay, which will be the focus of the second part of my talk. So the phenomenon that we're after in this line of work is how people use words to talk about what they see and want to do. Okay, for example, which objects are present in a scene, what parts those objects consist of, and even how to arrange those parts to create a new object. And a remarkable feature of human language is, of course, that it consists of individually meaningful tokens that can be combined in lots of different ways to achieve those communicative ends. So someone might, looking at these best-selling nightstands from the IKEA catalog, talk about the small rectangular dresser with 2 drawers each with 2 little circular knobs. But there's nothing in principle stopping that same person from reaching for entirely different words to talk about that same object, like the one with the 38 by 54 centimeter plank on top of the 68 by 38 centimeter plank, and so on. Or even invoking its unique product identifier. I know this because I actually looked it up in order, for this talk. Okay, so any object can be described in a huge number of different ways. So what determines why people favor descriptions at one level of abstraction and not another? So in this work led by Lionel Wong, Will McCarthy, and Gabe Grand, we propose that it might be useful to think of people as inferring from visual inputs a kind of mental graphics program containing commands that correspond to specific visual elements in their construal of an object. For example, perhaps in this program, a dresser function is invoked that takes a few arguments, such as how many drawers it has, the types of knobs, and so on, basically the specific attributes that characterize this dresser. And an appealing property of this mental graphics program is that it becomes natural to read out linguistic descriptions that reflect this structure. So the noun phrase 2-drawer dresser, just a mouthful, can be easily extracted from this program. But the problem, there's an infinite number of different graphics programs that could in principle render to the same image, and thus a quite rich hypothesis space of possible forms that this bridging abstraction might take, ranging from representations that invoke low-level graphics commands, like low-level primitives like lines and rectangles, to representations that invoke object-level chunks like that unique product identifier in the catalog. And so we formalize this variation in abstraction in terms of a concept library that contains the elements that are mentally accessible to a person, and then hypothesize that this concept library would be constrained to be representationally efficient. So to show you what I mean, consider this simplified 2D rendering of the dresser. Here are 3 different part libraries that could in principle be used to represent it. From the most compact on the left with just 2 functions to draw lines and rotate those lines, to the most comprehensive library on the right with those 2 base functions for drawing lines and rotating them, as well as more complex functions like ones that can draw an entire dresser with knobs, and even a function that can be used to draw this specific object in one fell swoop, like the IKEA Hemnes dresser. And then programs that you can write with these libraries would also look different. So with the leftmost library, the programs are necessarily going to have to be quite long since you only have lines available to you. Those are the only moves that you can make. With the rightmost library, you can get away with a minimum length program that invokes just the IKEA Hemnes dresser function. And for the library of moderate complexity, you're looking at programs written at a moderate level of abstraction. For example, the dresser function can be parameterized with arguments to tell you about its distinctive properties, like how many drawers it has and what kind of knobs, and so on. We hypothesized that the composition of the concept library that best captured how people carve up these objects to talk about them would depend on striking a balance between the overall size of this concept library sitting in their heads and the length of programs needed to represent the structural motifs appearing across the various objects that they encounter in that context. So to test that idea, we procedurally generated in this experiment 2,000 different objects. 1,000 of these were CAD drawings, CAD drawing-like images of objects from 4 different categories. And then the other 1,000 were these block towers made of these blue and red domino primitives. So here's just some examples. So you can get a sense of the kind of variation both within and between categories. You can see that we've nicknamed some of the subgroups within the drawings and towers by what we thought of them as evoking. And then what we did is ask people to write descriptions of several objects from each category that were detailed enough to allow someone else to then recreate the drawing or the block tower just based on that description. So that was the task, okay? And what I'm showing on the right is first the representational efficiency of different concept libraries, from the most compact to the most comprehensive. And we generally find is that libraries of intermediate complexity encoded objects most efficiently by balancing library size and program length together. Okay, so you have this U shape for representational efficiency. And then as it turns out, not only were those libraries representationally efficient, we also found a striking correspondence between the libraries that optimize representational efficiency with those that scored highly on their ability to predict actual human language, which we measured by fitting a machine translation model to align tokens of the underlying graphics program that we use to represent the objects to tokens of actual language that people produced in our production study. So note that this correspondence, where the dark green curve is maximized and the lighter dashed green curve is like minimized, okay, that correspondence, like that those coincide, that's not guaranteed. But what it suggests is that people generally prefer decomposing objects, carving them up into nameable parts that can be reused for many objects in that category. And a key prediction of our hypothesis is that what kind of encoding is representationally efficient then depends not only on the structure of any particular object that someone's describing right now, but also what attributes it shares with other objects that a person expects to encounter in that context. So in ongoing work, we are exploring how the concept libraries that are active in people's minds and then manifest in their language varies between different contexts with different data distributions, like different distributions of objects and their properties. So for example, in a world populated only with dressers, you might get pretty far thinking just in terms of, drawers and knobs. But if you're trying to generate useful descriptions for more of IKEA's diverse offerings, then you might justify activating a much larger library of simpler concepts to capture all of that structural variation that you might encounter. Okay. And even if that object distribution stays the same, though, the library that we use to communicate with others might evolve over time as we establish more common ground with other people. So what kinds of learning mechanisms might enable that kind of adaptation? So the final study I'm going to be sharing with you today also happens to be the basis for group project number 6, okay, which I'll unpack a little bit more. But just to highlight the key findings and the setup, in this study, this was led by Will McCarthy and Robert Hawkins with key contributions from Haoliang Wang and Cameron Holdaway. We tried to get at this question by pairing people up to now play this collaborative building game. One of the participants played the role of the architect and the other the builder. The architect could see the plans for the towers that they were supposed to build, see on the left, but they couldn't actually place blocks in the environment. The builder, on the other hand, couldn't see what the target scene looked like, but they were able to place blocks. So it was up to the architect to provide useful step-by-step assembly instructions, which they typed into a chat window, which the builder could then use to reconstruct the target scene. Okay, that's the setup. In this study, each target scene was structured hierarchically. So each scene contained 2 towers. Each of those towers consisted of 4 blocks. And then to see how behavior changed as participants learned to collaborate better in this building game, we repeated each of these scenes multiple times. And what we found was that between the first and the final building attempt, the language that architects used shifted to a higher level of abstraction, with references to individual blocks becoming less frequent. So the change in the frequency of literally the token block is negative from the first to the final repetition, but then references to entire towers emerged and became more frequent over time. So that's where these U, C, and L terms are coming online. And we modeled this learning behavior by combining 2 mechanisms. First, a mechanism for incrementally discovering recurring subroutines, like recurring patterns in the graphics programs that generated each scene across trials, in order to augment the library with, augment the library appropriately with new part concepts. And the second mechanism is one for coining new terms to refer to those new part concepts, basically aligning elements in the lexicon, like the kinds of words that people can say and the concepts that they can refer to. And we found that this conceptually simple combination of mechanisms yields an architect agent that can reproduce the key qualitative behavioral patterns from our behavioral experiment, including a bias towards tower level abstractions over time. So this architect agent learns to prefer these higher order terms rather than talking about individual dominoes. Okay, so this study is available for you to reproduce all the key results for in project P6, learning to communicate about shared procedural abstractions. There is a repo that's linked on the Cosmos website that is the main research repo. That's definitely still a good place to go to look at the full version history of all the code for this project. But if you're looking for more of like a guided experience, what we're offering is a series of 3 Python-based Jupyter notebooks that walk you through each of the main computational modeling techniques that were used in this study, okay? There's both an initial version, is tagged in the, there's a directory literally called notebooks_initial, okay, that are meant to introduce you to the relevant ingredients in that part of the paper, okay, that require you to fill in gaps in the code in order to proceed, okay? And then there's also complete versions of those very same notebooks and notebooks_complete with working implementations in case you wanted to check what you tried out against a reference, okay? These notebooks were custom built for Cosmos, actually. So please enjoy an enormous amount of effort over the past like 5 weeks, okay, from Will, Robert, and Zoe went into developing each of these 3 notebooks. So I hope you get a lot out of them, and like we really welcome feedback, because just in the past 2 years since we put out the CogSci paper, we realized that there are elements of this study, like different elements of the study resonate with different researchers in cognitive science in different ways. Like some people are more interested in the library learning part, other people are more interested in the convention formation part. We really wanted to be able to expose what the key concepts and technical parts of the project were, and like what was just like incidental to a particular study. So we tried to design these notebooks to be as friendly and in order to equip you with what might be useful to apply to your own work in the future. Okay, so notebook 1 looks something like this. It's focused on analyzing the natural language that we collected, including a bunch of the pre-processing that we did to the actual things that people typed in the chat window. And pointers to the various natural language processing libraries that you might use if you're working with free-form text data. Notebook 2 is focused on unpacking this concept library learning mechanism. So it's really, it gives you different ways of connecting elements of these graphics programs to how they render out and to actually build block towers. So there's like a cool module embedded in here that Will built that you can like build your own towers by like writing programs for yourself that you want to make, okay? And reproducing the library learning results in the paper. And then the third notebook is focused on the convention formation components, like how new tokens of language emerge that come to refer to those emerging part concepts that people reach for over time. Robert put a huge amount of work into basically writing parts of like a Python-based like distribution library, because it didn't really exist. And we discussed the usefulness of having like a Python-based way of engaging with this project rather than one that was based in WebPeople, which is a probabilistic programming language that we actually used for the experiments in the paper. We thought this might be friendlier, but in order to like recreate that, you have to like write an entire library from scratch for this. And all of that code actually is in the repo. A lot of the nitty-gritty is tucked away in some like utility scripts and files. But you can go and take a look at those as you go through notebook 3 if you're interested. Okay, so an advertisement for P6, okay? Oh, that changes everything. Oh dear. Okay, I'm sorry. P5. Okay, I thought I went this morning to see which one it was. Okay, so P5, okay. But there's like it's compositional_abstractions_tutorial in the Cog Tools Lab GitHub organization. I can share that link with anyone who's interested. But to finish up the like research talk portion, I shared with you some work exploring how people use visual and linguistic abstractions in a flexible way to communicate about the external world. And the larger goal here in digging into these multimodal generative behaviors is to understand how behavioral goals, what people are actually trying to accomplish, including communication, constrain the alignment between the contents of our perceptual experiences and the content conveyed by our communicative actions. And then it gives rise to a set of what I've been calling bridging abstractions that serve to link perception to action. So returning to the questions that posed at the outset, bridging abstractions are composable representations that are important because they support flexible multimodal behavior. They're useful not because they're static, but because they can be modulated systematically according to an agent's behavioral goals and can emerge and change even over brief timescales, brief social interactions. And third, evidence from our modeling studies suggests that these abstractions take the form they do because they provide useful ways of reformatting our experiences and plans in a way that's efficient for thinking and communication. Okay, that's all from me. Thank you all for listening.
For that amazing call. I have a question. I'm wondering how models like Stable Diffusion model emerging from the text to image neural networks would affect first of all the field that you're working in and maybe more generally how humans interact with visual contact and maybe more specifically with emerging field of prompt engineering. Where you don't need, so would it like increase our precision in like giving instruction or yeah, what is your
Cool, thanks for that question, very timely. So there are at least two like takes on your question that I am hearing. So one is, you know, we're living through this moment, this turning point in history, like in the history of cognitive tools, you could say, where people are able to create, you know, different representations of information in many more different ways, right? Including like the ability to actually efficiently explore the space of possible images via text, like via text-based interfaces is like, seems really powerful, right? It's really something that's very intriguing and that many different application areas are beginning to take up, okay? So that's like one read. Another is like as a cognitive scientist, how might we think about the relevance of these new emerging text-to-image, like multimodal systems as hypotheses about the kinds of latent representations that can support bridging between different modalities, for example, between the domain of natural language and the domain of all possible images, right? Okay, so the first one is really one that I think we're all living through and have yet to fully, you know, I think time will tell. Okay, that's like the cop-out answer. I think something that I find really exciting about the use of those tools at level one, the turning point in history level, is that there are these new tools may make it easier for us to study, say, cognitive phenomena that have seemed out of reach for a long time, that have like resisted rigorous empirical study of some kind. So for example, like I'm really excited about using these kinds of techniques and studies of visual creativity and collective creativity. I was having a conversation with one of my dear collaborators, David Ha, about the prospect of using these kind of text image models in groups. And like, because he made this observation that the kinds of memes that spread, right, like have certain properties. And the question is like, why do they have those properties? And how does the kind of curation, like the prompts generate, like the kind of like individually driven creation loop then interact with being embedded in a larger online community in order to identify these particular outputs that end up being really compelling and resonant with really large communities. And for people who may not identify as creatives, right, displaying this kind of casual creativity, as he's been calling it, I think that's really exciting and cool, okay? There's like the second level, which is thinking about, for these really large models, right? They tell us something about the size and shape of the solution space that allows you to connect these different domains. Not all of those solutions will reproduce biology, okay? We do not necessarily assume at the outset that any AI system, simply because it is powerful and can create outputs, can take inputs and create outputs that are in the same form and overlap with the distribution of human inputs and outputs, therefore is necessarily a good cognitive model, right? And so I think that's an open question. I think it's an open question that requires really like rigorous empirical benchmarking efforts that will not take place on Twitter, basically, right? You really need to design like very strong probes. For example, like this question of like, is the late representation learned by DALL-E and like other kinds of models like it? Do they have the kind of compositional internal organization that some cognitive scientists think really characterizes human thought? And I've argued for some version of that like today, right? Or not. I think those are open questions. They're really, really important ones. And then even if it turns out to be the case that what DALL-E is like on the inside, there's some similarities to how an individual human mind organizes language and visual representations, but not exactly. That'll be important. And understanding what those divergences are is also important because it tells us something about the space of possible ways of connecting data in really flexible ways. So hope that helps, speaks to what you're getting at. There's two mics, so
so towards the start, you could, for example, give an example of TikTok, right? And in that case, you have neither the communicator of this abstraction or the recipient.
Yeah.
And there's a lot of discussion in archaeology, like what do these things mean? Why did they make this art? I was wondering if you can take the approaches that you're using and somehow invert them or reverse them so that you can get back at like from the abstraction to how abstract is it actually, and maybe what is the meaning behind it, or why did they do this?
Yeah, no, it's a great question. I wonder, I want to ask follow-up questions about why you asked. Do you work in this area on those kinds of, okay, cool. So then you are likely potentially already familiar with some work that I'm a big fan of, have no involvement with, by Christian Thailand and Riccardo Fusaroli and other collaborators trying to understand how these marks that have been like etched into stone that have survived, in some cases, 100,000 years of erosion, right? And then pretty well preserved. So there's the kind of figurative illustrations that are famously in some of the caves in France and Spain. And there are also these other carvings that have come out of sites in South Africa that don't seem obviously figurative, but contain these geometric regularities that are also really highly suggestive of like someone intending to create some kind of like hatching pattern over time. It doesn't seem to be like an incidental byproduct of some other kind of like instrumental, like some other goal, you know? And I find all of these different artifacts really thought-provoking for all the reasons that you've raised, that to some degree the form that they take helps to constrain the space of possible likely intentions that someone had. So if someone is producing a figurative illustration of like a four-legged creature, right? Now, we can narrow down the space of possible intentions to ones that are probably communicating about something animate that takes the form of that four-legged creature, but the precise role that that particular artifact played in that community may be real. We may need like other sources of evidence in order to understand what's going on there, because we don't have the we can't ask the producer and the viewers from that time. But I think that a lot of what their work suggests is that there are these the patterns of variation, both like within cave and like within site and across different sites, where these visual artifacts and etchings and carvings have been recovered, suggest there's some like local cultural transmission. Like there are more similarities within the particular set of etchings and illustrations than like between different sites. And that can tell us something about the way in which those styles and the kinds of contents of those etchings and drawings seem to be a product of those social interactions, rather than being something that deterministically unfolds as like people organize in settled communities. But I think those are really fascinating examples of I take a lot of inspiration from data like those. And I suppose, your question is like, how do the kind of tools and approaches here like relate to those? And I think of there being an opportunity to use simulation, right? Use the tools of computational modeling, right? The ability to like run thought experiments about, well, what if the world were set up this way? What if the mind were set up that way? What if people interacted in this way versus that way? Do you end up with this particular kind of variation this kind of structured variation that we then go out and observe in real archaeological data, for example? I think actually building those bridges between models and those archaeological measurements is extremely valuable and cool. So I hope that helps.
Thank you so much. And also for all the effort put into your project. You might get a such assignment. My question is also about the architect builder project.
Yeah. So in our study, the architect saw what the actions the builder took in that bout of communication. So architects typed their message in the chat window. When they clicked submit, that entire message went to the builder. Builder saw the entire message, took however many actions they meant to take, and then that rendered for the architect.
So that was there cases where the architect gave instructions.
Yeah. So there are definitely cases of a kind of repair that the architect engaged in when the builder took actions that didn't actually correspond to the meaning that the architect was trying to convey. And I don't know, like I think that in this particular study, we had curated stimuli that we thought would be most likely for to see like a reasonably high level of accuracy. We didn't choose really elaborate scenes, but I could imagine like a design where we had stimuli that varied a lot more in complexity, where those kinds of errors were more frequent, and therefore like give us more power to look at the kinds of errors people make, like detailed error analysis, as well as like kind of repair type language that form. So yes, but like not quite in the quantities that you can get a lot out of it in this data set, but I think that they're like highly related versions of the study that could be useful. Yeah, we got time, right?
So you opened, I guess, with like some interesting examples of like cognitive tools, like not necessarily for communication, but for kind of discovery or kind of creation. And I was wondering, like, it seemed like that kind of thing requires like a slightly different like normative framework than kind of like the communication stuff. I was wondering what kind of framework or objective you think could fit, like or explain the development of those abstracted, like the Cartesian and the final.
Yeah. Yeah. Okay. So maybe for those in the back of the room, the question is about how to connect the opening examples that I provided, like the Cartesian coordinate plane, with the concrete phenomena that we ended up focusing on in the empirical work, namely like the use of certain kinds of abstractions for communicating with someone directly, right? So like what, perhaps the Cartesian coordinate plane is something where you might need other objectives in order to account for the form that it takes, other than communicative efficiency, for example. I end up toggling between different ways of thinking about that question that you raise. I guess this is part of the reason why, I think of all of these different cognitive technologies as supporting like thinking and communication, right? To some degree, like these are representational formats that took us many, many generations to discover. But once we did, we quickly, within a matter of a couple centuries, managed to have the expectation that the ability to become fluent in these abstractions should be accomplished. Like you should be able to acquire that ability in a few years early in life, like in middle school, right? Which is incredible, right? So there's something about this that is remote in some sense because it took such a prolonged search process in cultural evolutionary time, but then also is like learnable enough that we are able to teach these concepts in school fairly reliably. Okay. And I think that, in some sense, like in order to have a system that's like good enough to be able to onboard new users of that system in every generation, it's got to be good at communicate. Like it's part of it is it's like expressivity and also learnability, and which is really, I think, related to how well it's able to communicate, right, certain kinds of abstractions in a way that like people are ready to learn, right? People are ready to learn and continually bootstrap over other experiences they have into using these kinds of graphical abstractions, right? So I'm trying to find like a less roundabout way of trying to address your question. It's like there's certain ways in which these are used, like these are clearly used for reasoning, maybe even by a single individual trying to work through a problem. And you can construe that as being totally separate from communication because there isn't someone else involved. But to some degree, it's like some way of like linking what's on the page and what's in your head in a way that like, I guess the null hypothesis is like the representational forms that make that kind of exchange more fluid and precise is also those kinds of forms that are also easier to communicate with other people. Like those forms that support clear thinking are also those that are useful for clear communication. And that's like the null. And then there may be some cases where there are these like, idiolects that people use just to privately think about things, and like they may be quite idiosyncratic and very different from what ends up being really shareable and useful to others, which are also interesting. But I would bet that the lion's share of the phenomena that I'm calling these cognitive technologies are in that overlap between what supports like clear thought and coordination with others.
One more question.
Hi, so great talk so much. So kind of going back to what you're saying about how people communicate at different levels of abstraction adaptively, with like for example, pictures, I'm kind of interested in how I hope this makes sense. Kind of looking at aesthetics, how because in a sense I feel like aesthetics disagree, but I feel like there's a communicative aspect of it. Where it can be like adaptive, and yeah, I guess I'm just like curious how people think representing things at different levels of abstraction aesthetically for us. Yeah, thinking about like pretty evil.
Yeah, no, thanks for that question. think throughout this work, I've like quite self-consciously styled it to be like more sterile and austere and cognitive, right? Then I think, even like I privately wish it were. Like in some sense, like I'm drawn towards these phenomena partly because of their role in like how we represent knowledge and share knowledge with others, but also because like they're sources of great beauty and feeling, right? That like the artistic traditions come from the application of such technologies, right? To communicate things other than like what label we should use to refer to something, right? And so in your question, so aesthetics, of course, a really rich concept, picks out many different particular phenomena, right? So there's a part of it that I heard in your question around like elegance, right? There's like something about like elegance and economy of expression that can be part of what we think of, especially in science, what we look for in, let's say, figures and diagrams. And I think that's a component of aesthetics that feels like ready to be accounted for by these kind of like information theoretic approaches. Okay. There's another like large swath of maybe what people think of when they think of aesthetics, which has to do with the communication of things other than like semantic knowledge, for example, like phenomenal experience. Like, what does it feel like to be a person, right, with these memories and these prior experiences? And how can I create, I think it's like a really fascinating way of posing this question is like, how can I create a picture that not only communicates the identity of like an object or like identity of a person, but also what it feels like to be that person, right? Which ends up needing to be something that is like encoded in the brushstrokes in a painting, for example, but isn't like, it's like communicating about something like affect and like phenomenal experience, right? And I think that that's a really cool and exciting frontier that honestly has also felt thoroughly intimidating. I haven't really felt brave enough to wade into yet, but I think it's, provides a lot of inspiration for the kind of work that we're doing.